Hello, welcome to this video. Is where the actual chemistry is going to start. We've been studying the more like the introduction to chemistry, but this is where the actual chemistry is going to start. But don't think this is something new. This is the continuation of the understanding that we've gathered in the previous topics. We're still studying the nature of matter. So this video, which is language of chemistry, is going to be discussed by using this topic map. So of course the topic map just gives us an idea of how concepts are connected. So we're going to start with elements, mixtures, and compounds. When we're studying kinetic theory, we learned that matter is made of small, discrete, or separate particles. So those particles can be viewed for now as elements. So these elements can be combined to form mixtures or compounds. So we're going to study elements and how mixtures are formed from elements and how compounds are formed from elements, and also the difference between the two. When we do that, we're going to go deep into elements. We're going to ask ourselves, what is it that makes up an element? And we're going to learn something called an atom. And when we are studying atom, we're going to study something that is part of the structure of an atom, which is very important because it determines the behavior of an atom, and they are called shells. So these shells have got important particles that we're going to study that determines the behavior of an atom. And there's because of the same particles on shells, atoms behave in such a way that they can change from being an atom into being what is called an ion, because of the same behavior that we're going to study. Then we'll wrap up this topic or this video with an introduction to a very important tool in chemistry called the periodic table. So we start with elements. What is an element? An element is defined as a pure substance which cannot be split into two or more other simpler substances by any chemical means. Meaning that if you have been given an element, you cannot break it apart into other simpler substances by any chemical means. What are examples of elements? Examples of elements of iron, copper, and oxygen. Iron, copper, and oxygen. So we're familiar with these things, but can't we break them as the definition demands? So let's take a look at iron. A common example of iron are iron sheets. Can't we break iron sheets? Yes, we can break them. If they are big, we can break them, get smaller iron sheets. But the definition says by any chemical means. By any chemical means, which means when you break that element, it should give you new things. So when we break iron, we're going to get something else. We still are going to get ions. So if we keep on breaking iron sheets, we'll still be getting iron sheets or smaller iron sheets. We won't get something new. We won't get copper out of iron. We won't get oxygen out of iron, which are other elements. So that's what this definition means. You cannot split an element to get other simpler substances by any chemical means. So the diagrammatic representation of an element is this, which you might be familiar with as we were studying kinetic theory. We talked about these things inside substances. So this can be a substance, then these are the elements. This can also be another substance with these elements. So the difference in colors is just for illustration. I just want to show you what happens when we mix these two elements, the elements in this substance and the elements in these substances. In this substance, I mean. So so mixing of elements can give us a mixture, which is defined as a substance which consists of two or more elements physically combined. So if we physically combine elements, we get a mixture. Remember, we studied mixtures in the when we were talking about solutions and crystals. So of course we have got that definition and also this definition. Both of them are correct, but this one has been put here so that we understand the context, or we understand how mixtures come in when we're talking about elements. So here I emphasize on the word not chemically, meaning that by physically combined, it means the combination is not in any way chemical. So this is how a mixture is represented diagrammatically. So we have different elements here. If this is zig or sugar, or it's called what, sugared water. Yes, zig, sugared water. Yeah. So if this is sugared water or zig, yeah. So these are, these can be elements of water, and this can be, it sounds weird, elements of water, due to a reason you're going to understand later. But anyway, we can say these are the particles of water, and these are elements of sugar, or particles of sugar. So the way they are combined is like this. They are not in fixed proportion, meaning that when you're making ziggy, it doesn't matter how much sugar you put in it or how much water you put in it, it's going to be ziggy regardless. So that's one important thing we can get from here. So substances that makes up a mixture are not always in fixed proportion. So we can have a lot of these black elements and less white elements, but at the end of the day, we're going to get a given mixture. Then another thing that can be made when we mix elements chemically is called a compound, and is defined as a substance which consists of two or more elements chemically combined. So one thing about a compound is the properties of a compound are different from those of individual elements. What does this mean? So when you make a compound, you cannot tell what makes it up just the compound, just by looking at the properties of a compound. A good example of a compound is water. So water is made of gases, two gases which are combined, hydrogen and oxygen. So when you look at water, you won't see oxygen or hydrogen, or you cannot have physical properties that are related to hydrogen or oxygen. So that's what this means. Water is a liquid, hydrogen is a gas, oxygen is a gas. But when we mix them, forget about when we mix them part. So water is a liquid, hydrogen and oxygen are both gases. They have different physical properties. So the properties of a compound are different from those of individual elements. The other property of a compound is the particles of elements are combined chemically in a fixed ratio. Remember, when I was talking about a mix, I talked about combination that is not always in a fixed ratio. In a fixed ratio, it means if you put two spoons of sugar, you have to put maybe 1 cup of water for it to form a zig. And if you put more than 2 spoons, it means you have something else, you won't have zig. So for a mixture, it doesn't matter how much you put, but for a compound, you have to put the same number of elements. So what I mean is, for you to form a compound, for example, water, you need a fixed amount of hydrogen and a fixed amount of oxygen to be combined. For example, to be specific, for water, you need 2 atoms of hydrogen and 1 atom of oxygen. So sorry, I've used the word atom, which we haven't discussed, so let me just rephrase that. So for you to form water, you need 2 elements of hydrogen and 1 element of oxygen. So when you combine this 1 element of oxygen and 2 elements of oxygen, you're going to get water. If you increase the number of elements of oxygen to be 2, then it's something else. So the properties of elements, the particles of elements are combined chemically in a fixed ratio. So that's what it means. It is difficult to separate a compound into its constituent elements. So that's one property of a compound. If you remember, we studied separation techniques, where we learned how to separate elements of a mixture. So for example, ziggy, we can separate sugar and water, but for a compound, it's not easy to separate elements that makes up a compound. So this is a diagrammatic representation of a compound, always made up of the 2 elements chemically combined. So this is how chemical combination is represented. These are chemically combined, these are chemically combined, these are chemically combined. And this combination is called a chemical bond, and we're going to start that. So this is how a compound is represented. So now let's take a look at the difference between a compound and a mixture. We just do a table where so mixture compound. So here, the substance in a mixture can be separated by physical means, while the elements in a compound cannot be separated by physical means. 2, energy is not usually given out or absorbed when mixing occurs. So when you're forming a mixture, then there is no energy that is given out or absorbed. But when you are forming a compound, energy in form of heat, light, or sound is usually given out when a compound is formed. So when you mix two chemicals, there will be, maybe they can be, you can see a light, or I know when you think of chemicals, we always think about things of frames based things. So that's the energy we're talking about. When you are combining elements to form a compound, usually there will be sound, there will be heat, there will be light. But for a mixture, we don't have that. The properties of a mixture, such as color, density, weight, sweetness, are an average of those of the substances in it. What this means is the sweetness of your ziggy or of your sugared water always depends on how much sugar you've added and how much water you've added. So they are in between the two constituent elements or the constituent substances. Well, for a mixture, the properties for a compound, the properties of a compound are quite different from those of the elements in it. For example, like I said, water has different properties as hydrogen and oxygen. The composition of a mixture is variable, and the composition of a compound is fixed. So this one I explained. So going deep into an element is made of what is called an atom. So this is how an atom, in a simplistic way, can be represented. So let's just study it. So the at the center of an atom is this thing here. If this is an egg, you can look at this to be more like a yolk, the center, the heart of an atom. So this is called the nucleus. Inside the nucleus, we've got two particles. So normally inside the nucleus, we've got two particles. The first one is called a proton, which is always positively charged. So this proton always has a charge of plus. Then this one is called a neutron, and its charge is 0. It doesn't have a charge. So it has a neutral charge. It is neither negative or positive, hence called neutron. Then outside the nucleus are what are called shells or energy levels. So this is a shell here. So an atom can have more than one shell. It can have another shell here, another shell on the outside, just like that, depending on the type of atom. So in the shells are particles, these ones here, which are called electrons. So electrons are negatively charged. They are opposite of protons. Protons are positive, electrons are negatively charged. So these are electrons which are in the shells. So one thing about atom is the number of protons is equal to the number of electrons. If we have one proton here, we have one electron here. If we have two protons here, we have two electrons here. If we have three protons here, we have three electrons here. So if since this is positively charged and these are negatively charged and they have opposite charges, if we have three protons here, then the charge here is going to be positive 3. And here, if we have 3 electrons, then the charge is going to be negative 3. So if we add positive 3 and negative 3, you get 0, meaning that the resulting charge of the entire atom is 0. In short, an atom is not positively charged and it's not negatively charged. So from now, let's go deep into the atom. By the way, don't get confused by my illustration. Here there's one proton and here there are 2 electrons, but I said the number of protons must be equal to the number of electrons. So normally, if this is a real atom, there are 2 electrons here, which means we must have 2 protons here. So we must have one proton here and another proton here. So let's start some properties of these 3 particles: the neutron, the proton, and the electron. Fundamental particles of an atom in details. So we'll start with the electron. Yeah. So an electron has a negatively charged particle. It has a charge of -1, and it has a mass of 1/1840 atomic mass unit. So atomic mass unit is the units for the particles that makes up an atom. So an electron, its weight, or its mass, I mean not weight, it's 1/1840. So if you punch this on a calculator, you're going to get 0.0 something. That is its mass. So what to take from here is it has a negative charged particle, which is -1. Then the second one is the proton, which is which has a positively charged, which is positively charged, which has a charge of +1, and which has a mass of +1 atomic mass unit. So the mass of a proton is +1, while that of an electron is 1/1840. Then the charge of a proton is +1, while the charge of an electron is negative. Finally, we have the neutron. So the neutron has no charge and it has a mass of +1 atomic mass unit. The mass of a neutron is the same as the mass of a proton, which is +1, +1. The mass of an electron is 1/1840, and if you punch that, you're going to get a very small number. So when you are trying to represent the mass of an atom, we usually just add the mass of the neutron and that of a proton, because that of an electron is very small. So we're going to learn some terminology and symbology. We're going to start with proton number. So this is the number of protons in the nucleus of an atom. Its other name is atomic number and is represented by the symbol Z. So if an atom has 5 protons, then its proton or atomic number is 5. Then there is another interesting one which we need to know, which is number of neutrons. For this one, we don't have a special name, but it is represented by symbol N, which is just the number of neutrons in a given atom. Then there is also mass number. So mass number is more like the mass of an atom, which is just the combination of the proton number and the neutron number. So the definition is it is the sum of protons and neutrons in the nucleus of an atom, and it is represented by the symbol A and given by the formula A is equal to proton number plus number of neutrons. So here are the first 5 elements. So we're going to be studying elements from here onwards. So here are the 5 elements, the first 5 elements. So elements are arranged according to their atomic number. We're going to learn about the arrangement of elements in the next video, which is the periodic table. So the first element is hydrogen. Its symbol is H. Its atomic number is 1. Its mass number is 1. For its mass number to be 1, it means it doesn't have a neutron. It only has a proton. Then helium is represented by He, and keep in mind that for elements with 2 letters whose symbols have 2 letters, the first letter is a capital, the second is a small. So helium has an atomic number of 2 and the mass number is 4. Means that for the mass number to be 4, it means the number of neutrons are 2. So it has got 2 protons and 2 neutrons, which gives us 4. Then we've got lithium. So lithium symbol Li, atomic number 3, mass number 7. Beryllium has got the symbol Be, atomic number 4, mass number 9. Boron B, atomic number 5 and mass number 11. So from here you should be able to tell how many electrons, for example, boron has, how many protons boron has, and how many neutrons boron has. So atomic number is just the number of protons, so it has 5 protons. Then the number of protons is equal to the number of electrons, which means it has 5 electrons. Then the number of neutrons is the number that is added to 5 to get 11, which is 6. Or in short, 11 minus 5 is 6. That's the number of. So we're going to concentrate on what is called nuclide notation. So this nuclide notation is the easiest way to represent the number, the symbol of an element, the number of protons, the number of the mass, the proton number and the mass number of an element, which gives all of an element or an atom, which gives you all the information you need to know about a given atom. So usually the nuclear notation or elements are represented by this. So this will be the symbol of an element. For example, for helium it's going to be He. Then on top we're going to have the mass number, and on the bottom we're going to have a proton number. So the way I've written it differs. Others usually actually the mass number is written here on top and then the proton number here, but others might write the mass number here and the proton number here. So just know that whatever is on top is the mass number and whatever is on the bottom is the proton number. So here are some, these are just two elements, but I want to show you an example using helium. So I want to write the nucleic notation for helium, which has the symbol He, meaning that here where there's X we put He. Then atomic number here we're going to put 2, and the mass number here we're going to put 4. So we write this as helium 42. Again, if you write 4 here and 2 here, it's okay, or you write 4 here and 2 here, it's okay. So we're going to learn about something interesting called an isotope. So listen to this. An element can be made of maybe more than one atom. So in a situation where we have an element with 2 atoms, the atoms should be the same. In short, if we're talking about hydrogen element, let's say hydrogen, it means the atoms that makes up hydrogen must be the same. By the same, I mean they should have the same mass number, the same proton number. But it's not always the case. There are some situations where an element has got atoms that have the same proton number but different mass numbers. In short, they have the same number of protons but different number of neutrons. Such kind of atoms of the same element having the same proton number but different mass numbers are called isotopes. And these are the ones we're going to study. So isotopes are defined as atoms of the same element having the same number of protons but different number of neutrons. By different number of neutrons, it means the mass number is going to be different, because mass number is the sum of proton number and number of neutrons. So this is the point. So here is one example of an isotope, carbon. So carbon is made up of 3 different atoms, or in short 3 different isotopes with different names, different nucleic notation, because they have different number of neutrons. So the first one is called carbon 12. Sorry for that. The first one is called carbon 12, and the nucleic notation is, we write C, then we write the atomic number 6 and the mass number 12. Then it's from here we can say the number of protons is 6 and the number of neutrons is 6, because 6 plus 6 will give us 12. Then we also have carbon 13. Again, the mass number are different. This one is 13 and the proton number is 6. So number of protons is 6 and number of neutrons is 7. Carbon 14, this is its nuclide notation. Again, it has 6 protons and the number of neutrons, we just do 14 minus 6, which is 8. So these are isotopes. Same proton number, different mass numbers. So here are some uses of isotopes. Isotopes have got some good uses. One of them is hydrogen isotopes are used in the study of nuclear reactions. So isotopes have got good behaviors, which makes them good for such studies, which are nuclear reactions. Another use of isotopes, there's cobalt isotopes, which are used in the treatment of cancer. So cobalt isotopes are good when it comes to. So we're going to finish this by studying what are called relative atomic mass. Relative atomic mass. So what is relative atomic mass? So we're going to understand the concept of relative atomic mass by understanding these 2 isotopes. So when we have the same kind of same kind of atoms in an element, not isotopes, because isotopes are different atoms of the same element. So if we've got the same kind of atoms in the same element, meaning that they have got the same mass number and the same proton number, it is easy to represent the mass number and the proton number of that element. Why? Because if this is carbon 612 and this one is carbon 612, these are different atoms, then the element, you can just represent it the same way as carbon 612, which is just a representation of the average of the mass numbers and the proton numbers of individual atoms. But what about this case where we have one is carbon 12,6 and the other one is carbon 13,6? So what number are we going to use to represent carbon? For the proton numbers, they are the same, it's okay. But for the mass numbers, it's going to be tricky. So we need to get the average. So we don't get the average by adding 12 plus 13 divided by 2 for those who know the average, there is a formula we use, and what we're going to get is called relative atomic mass. So the definition for relative atomic mass is it's the mass of one atom of an element compared to 1/12 of an isotope of carbon-12. So don't get confused on what this means. Is in short, there is a standard which is used to compare the mass, the relative atomic mass of an atom, and the standard is carbon-12. So this is just a standard. So this is the definition that you can just master. There will be no concepts that are going to be derived from this. So the definition for relative atomic mass is the mass of one atom of an element compared to 1/12 of an isotope of carbon-12. But what is important is to know how to calculate relative atomic mass. So its symbol is AR, and the formula is this. Looks complicated but very cheap. So relative atomic mass is equal to mass of isotope 1 times percentage abundance over 100 plus mass of isotope 2 times percentage abundance over 100. What is percentage abundance? Percentage abundance is nothing complicated. It is how abundant is a given isotope in a given element. So if we have an element, then in the element there are two isotopes. So each isotope has got its own abundance or percentage abundance, or how much of it is available in that given element. Hope you get the concept. So we can have this isotope 1 and isotope 2, but the element might have a lot of isotope 1 and less of isotope 2. So we need to know how much abundance is isotope 1 as compared to isotope 2 to know the relative atomic mass. Again, a little bit deep but very cheap, as you are going to see. So here is an example. The two isotopes of chlorine have the following percentage abundances. Chlorine 35 has 75% abundance and chlorine 37 has 25%. So chlorine 35 is an isotope of chlorine and it has a percentage abundance of 75, and chlorine 37 is also an isotope of chlorine, but its percentage abundance is 25%, meaning that in chlorine there is more of chlorine 35 than chlorine 37. So what is the relative atomic mass of chlorine? So to calculate the relative atomic mass, we apply the you forgive me because of space, so 1 is down here, but the formula is supposed to be here, but because of space I've just written it here, but you're going to see. Relative atomic mass is atomic mass of chlorine 35 times its percentage abundance plus atomic mass of chlorine 37 times percentage abundance over 100. So the relative atomic mass is going to be, so what is the atomic mass or the mass number of chlorine 35? It is 35, because if they say chlorine 35, we use the mass number as the number here. It means its mass number is 35. So it's 35 times percentage abundance. According to the question, the percentage abundance was 75%. So we do times 75 over 100. We go to chlorine 37, its mass number is 37 times percentage abundance, which we are given, which is 25 over 100. And when we calculate this, 35 times 75 divided by 100, we're going to get 26.25 plus 37 times 25 over 100 is going to give us 9.25. And when we add, we're going to get 35.5. So this is the relative atomic mass of chlorine. So sometimes they can ask you, why is it that the relative atomic mass of chlorine is a decimal instead of a whole number, or it's a fraction instead of a whole number? Why can't it be 35 or 36? Why is it that it is 35.5? The answer is simple, because the relative atomic mass of chlorine is the average of the atomic masses of its isotopes. So this marks the end of this introductory part to language of chemistry. I hope you have learned a thing or two. Otherwise, happy solving.